Hello and welcome. I hope you are having a great day. In this video, we are going to discuss about chi-square test. So this is another test very useful for hypothesis testing, and within this we will discuss about chi-square, goodness of fit test, and test of independence. So these are the most important chi-square tests, and generally this is also called Pearson's chi-square test. This is because of the scientist who has contributed a lot to this test. So let me set up the agenda. So first we'll understand the chi-square distribution, because most of the tests they get the name from the underlying distribution. So based on the test statistic distribution, the test name comes. So this will the chi-square test uses chi-square distribution. So first we'll understand what is chi-square distribution. Then we'll understand that how it is used for for categorical data, and how categorical data it is modeled as multinomial, and then for a very large n this can be approximated as a normal distribution for categorical data. We'll understand that how it happens. Then we'll understand the chi-square test statistic and the chi-square test. Then we'll go specifically and understand goodness of fit. What is chi-square goodness of fit test? And then I'll just mention some other goodness of fit test which is good to know. You should just go and look it up. And then we'll talk about chi-square test of independence. Okay, mostly if you check Wikipedia, if you talk about chi-square test, then they will point you to test of independence. Okay, so let's begin. So let's go one by one. So the first thing, that is, what is chi-square distribution? This is another distribution. As I mentioned, there are a lot of distributions and you cannot remember all of them, and there are a lot of tests for also. So these are some important, and depending upon your use case, you can go and search online and you will get your corresponding test and the distribution. This is one of the most common, so we are discussing this. Okay, let's see. So what is chi-square distribution? So a random variable q is said to follow a chi-square distribution, if it can be denoted as sum of squares of n independent standard normal distribution. Okay, so for example, so what is a standard normal distribution? So this is n01. Let me do. So this is a standard normal distribution. Standard normal distribution. So this is standardized. So we know this. So I was telling you the actual definition. Let me tell you in simple terms. So we have such standardized normal distribution, which is mean centered and variance scaled. So your mean is centered to 0, and your variance, that sigma square, is scaled to 1. So you have this, and you have n such independent random variables. Okay, when you have n such independent random variables, and when you take a sum of that, and the distribution that you get out of that, those squared sum of these standard normal distributions, random variables, that distribution is called chi-square distribution. So it is written as, so the symbol is a fancy x. Let me use a different, like this, chi-square, and it is also has a degrees of freedom. I'll talk about this. I've talked about this in t distribution also. Okay, so this is the same degrees of freedom, and this is equal to summation I equal to 1 to n zi square, and this I is, so if you expand it, this will be z1 square plus z2 square plus so on till zn square. These are n independent standard normal distributions. Simple. Okay, you just square them and add them up. So we know the properties of this, and we just square them and add them up, and the distribution that you get out of this, that is called chi-square distribution. As simple as that. Okay, and it has degrees of freedom also. And what do you mean by degrees of freedom? So degrees of freedom, I'll give you an example that will make it clear. So I have discussed this in the t distribution also. I'll tell you again. So degrees of freedom, let's understand with an example. Say for example, you have 10 observations, 10 data points. Okay, and the sum of the 10 data points is equal to 50. So now if I take the sum of 9 sum of 9 such observations. Okay, So these can be any 9. So these choices will be independent. I can take any such 9 choices and these choices will be independent. But the 10th one will be dependent on these 9. How? Because the 10th observation will always be fixed. This will be, the value of this will always be equal to 50 minus some of the other 9 observations, right? So how many of these can vary independently out of this 10? Only 9, because the 10th one will always be equal to, say for example, the sum of the other 9 observations are 45. If I take sum, then the 10th one will automatically be fixed to 5, right? And see, if I take other sample, other set of 9 randomly from there, and the sum comes out to be 42, then the 10th one automatically becomes 8. It is not independent to take some other value. If this is 42, it cannot take 10 because the sum is fixed to 50. We know that. So because of this, the degrees of freedom, because the number of observations or the data points that can exist independently, they are 9 only. That is, if the total number of terms is n, then the degrees of freedom, that is denoted by kind of v, will be equal to n minus 1, because the last term or the nth term is dependent on the n minus 1 terms, other terms, and only these can vary, and the last term will always be fixed. I hope this is clear. I've explained in other video also, and again this should be clear again. So if this is clear, so let's proceed. And always in most of the distributions, the CLT will come. CLT is your central limit theorem, so we'll use this again. So why central limit theorem coming here again? So we'll make use of this. So what does central limit theorem say? So let's remind ourselves. So this n is this n. So this n is for this degrees of freedom, and this is your zeta square. Okay, so this is your chi-square distribution. Then we understood what is the n for this, and now let's proceed further and bring into picture central limit theorem. We'll understand this, and I'll tell you why am I discussing about it. So what does central limit theorem state? That if you take the sampling distribution, if you have any data point, right, and if you take the sample mean, okay, if you have multiple samples, say for example I have first sample and there are like x1, x2, xn, and that sum is sample mean is x1 bar. Then you have second bucket which has again n is xn, n samples. The sample size is n. Okay, so this is your x2 bar, and then you do till kth. Okay, and then again you have these terms, and this comes to xk bar. Now if you plot these, this is a sampling distribution of the sample mean. If you plot these, you will get a normal distribution. This is what central limit theorem says. As n becomes very large, generally large is n is greater than or equal to 30 is considered large for practical purposes. But if n is large, this will approach a normal. As you go, n becomes higher and higher, this will become a better normal distribution. Okay, that's what is central limit theorem. So the sample mean will approach a normal distribution, and other details of this I have captured in another video, which is central limit theorem video. I'll put a link of that video in the description. Okay, so sample mean. So what is the mean in general? So whatever mean is the average. Okay, this is the average, and generally this is like sum of all the values divided by the number of items in that. So if this is following, if this this term follows a normal distribution, then if I take out this division, so even this sum will follow the normal distribution, right? I'm just multiplying by dividing by some number. If I have some n data points and they are following a normal distribution, and if I remove this division factor, whatever the scaling factor, still this will follow a normal distribution, right? Only the scale will change. So what I mean to say is that if the sample means are following a normal distribution, then the sum or the count in case of categorical data, they will also follow a normal distribution. That is the main takeaway from this. Okay, so if this is clear, let's move ahead. So just keep this in mind and we'll come back, because this chi-square test is used for categorical data. Okay, categorical data where we cannot have some number 1, 2, 3. For example, if you have success, failure, or if you have multiple classes. Okay, say for example, if you have multiple classes of animals and you are trying to okay, compare them, or you have gender, male, female, or if you have product which is defective or non-defective. So these are categorical variables. So only you can have the count of each category for comparison. Okay, they cannot be compared directly. Say for example, if 1 and 2, you can compare 1 and 2 directly. But if you have categorical data, you cannot compare them, and then we take the count of that and then we compare them. So that's why categorical data is different. I hope that is clear. So what did we understand from central limit theorem? If the mean follows a normal distribution, then even the sum or the count will follow a normal distribution. And this count factor I'm bringing because we are dealing with categorical data, which we generally count and then we make observations based on that count. Okay, so let's move. Let's come back to this thing. So these things are clear. So let's come back to the chi-square distribution. So I'll mention some properties of this. So what are the properties of chi-square distribution? So this is simple. Some properties. So this will always be non-negative. This will always be non-negative, right? Because this is sum of squares. So that is obvious. So sum of squares will never be negative. So this will always be non-negative. And then the distribution, when you plot the distribution, this is asymmetric. This is not like normal, which is symmetric. Generally, it's skewed towards the right. I'll show you the picture of that. Okay, that is skewed towards right, and the shape depends on, as t distribution, whenever we have degrees of freedom, the shape depends on your degrees of freedom. So as the degrees of freedom change, the shape will change. Okay, and as the degrees of freedom increases more and more, it will become more and more symmetrical, and it becomes very large. It will be very close to the normal distribution. It will become symmetric. Let me show you the distribution. I have opened it here. This is your Wikipedia. This has become very small. This is chi-square distribution, right? Yeah. Okay, let me take a screenshot of this and I'll just show you. So you can see from here itself. I'll highlight this in my notes, that the distributions for different degrees of freedom, right? You have different okay, the k here is the degrees of freedom. Okay, so let's come back to the note. I have brought it here. I have the note is visible. Okay, so this k here, this is for degrees of freedom, and you can see that as k changes, it is becoming more and more kind of symmetrical. It is becoming, and if you can see that is skewed towards the right. That's what I wanted to show you. This is the kind of distribution. So all the distributions are not symmetric. Even t was symmetric. So I wanted to expose you to another kind of distribution. Okay, so just have a look. This is skewed towards right because the tail is more towards right, and this is here the peak is there. Okay, so next let's discuss the chi-square test, and before that let's understand the chi-square test statistic and why is it important to understand that. So we have categorical data, and that's what we have understood. Okay, so we have categorical data. Okay, and that's what we are dealing with. These are not numbers. So here what we do for categorical data, we have count. We count, and there can be multiple categories. For example, if you have a Bernoulli trial, right? Bernoulli trial. So it's binomial. It's binary, success, failure, right? And you remember the generalization of Bernoulli was binomial. For n trials, it was binomial distribution, and similarly the extension of binomial is multinomial distribution, where you have, this is for n trials. So here you have n trials, but here you have only two categories. Here you have k categories, or okay, say k categories. So these are the known distributions. We have studied Bernoulli and binomial in one of the videos. I'll put the link of that in the description if it's not clear. Okay, so in Bernoulli trial we have success failure, like tossing a coin, and if we toss a coin n times, for capturing the number of times or the total number of successes, we have binomial distribution. And similarly, if we have more than one category, then it becomes multinomial, and we have n trials for those n categories. And all this categorical data, because we can have many categories. So for example, if I'm comparing the height of three species of dog, okay, if I'm comparing their weights of 3 species of dog, species 1, species 2, species 3, so there are multiple these weights will be there. But if I'm comparing some other feature, there is some other feature, and I have the category of that dog, 1, 2, 3, which category this dog belongs to, and I can have only the count, the number of pets people have, okay, what category they have. So if I'm taking that, so I will have only the count of that particular category. So that's where this numerical analysis won't be helpful, or using a t-test or a z-test won't be helpful, and this becomes a categorical data. For example, if you have a male, female, others, gender, we are filling it in a form, right? Then we have to count what is the count of each gender, and depending upon that we make decisions that what is the vacancy, etc., for a job. Okay, so we are modeling this categorical data as a multinomial. So if you know multinomial distribution, so if you check that, the expected value of the ith category is equal to number of, n is the number of trials, right? N is number of trials, n is equal to number of trials. Then the expected value will be n into probability of the ith category. I is the ith category. There can be, I can be 1 to k. Say for example, sigma pi, I, like this is 1 to k. There are k categories. This will, the sum of all the probabilities will be 1. For example, if you have binary and we have heads and tails, and generally if it's a fair coin, then it will be 50-50, half. So the probability sums up to 1. Even if in the multinomial category there can be more than one category, and the sum of all the probabilities should be 1. So your expected value, or for the ith category, or this is also your mean. Okay, this is your mean. Let me write it here. This is the mean, and similarly there will be variance. Okay, variance for the ith category. So this will be expected value of I into 1 minus pi. So this is your npi into 1 minus pi. So this is your multinomial. This is coming from your multinomial distribution. Okay, so we have this. So now again we'll apply central limit theorem for very large n, because this chi-square test is for very large sample size. Okay, we need very large sample size. So we have very large sample size, and now this we have multinomial distribution. So according to central limit theorem, as n increases, this n number of trials increases, this distribution, multinomial distribution, so this will be this is a discrete, right? This is a discrete distribution. So as n increases, we can approximate it as a normal distribution. Okay, so this the observations for each category. So observation for ith category was not theta. So if the observation, whatever is the observation of the count for ith category is equal to OI. Okay, if we are having this, then as n increases, so according to central limit theorem, this multinomial distribution can be approximated as a normal distribution with same mean and variance. So this is your mean, this is your variance. So what will be your, for large n, the count of the ith category can be approximated as a normal distribution. So this is approximation to a normal distribution with mean npi and variance. This is npi into 1 minus pi. This is also your expected value of I. Okay, so this is your, this can be approximated as this. Okay, so now we have a normal distribution. We have approximated from a multinomial, we have come to a normal distribution, And as soon as we are normal distribution, we know a lot of things about it. We can do a lot of information. So we have, once we have normal distribution, we can think of z-scores now, what we discussed in z-test video. I'll put the links of those also in the description. So what does the z-score measure? It measures how many standard deviation is a data point away from the mean. Okay, it measures the distance from mean. It measures the distance from mean in standard deviation, in terms of standard deviation. Okay, for a data point. So for example, if I have this, this is your normal distribution and this is your mean, whatever is the mean, and say for example, if I have a data point here, then in terms of standard deviation, how many standard deviations away this data point is. So this, for example, this is your x data point. So how many standard deviations away this data point is, the z-score will give you that information. And then we can have a z-score is a standardized score. Standardized means mean centered and variance scaled. Standardized. This is your, whatever is your expected value, whatever is your observed value minus your expected value by square root of variance of the ith category, right? We divide by the standard deviation. This is square root of variance. So that's what, this is your observed or x bar for sample mean, and here we have counts, right? So this is your observed count for ith category. This is the expected count for the ith category, which I am getting from this multinomial trials. Okay, whatever is the category, and then we have the variance. This is your mean centered and variance scaled. So this is your expected value is your mean, and the square root of variance is your standard deviation. We know this. So we just subtract it from here and we divide it by the standard deviation, and this is standardized now. So this standardized score is called ZI. ZI is equal to observed count of the ith category. We have multinomial data, expected value by square root of variance of the ith category, whatever is the variance. So what are those values? Let's put them and just keep them. OI minus NPI by square root of NPI into 1 minus PI. So this is what we'll get. But there's a catch. So this is your ZI. So we have got a ZI is, so this is standardized means this is your, this will be here N01. Okay, that is mean centered and variance is scaled to 1. So whatever, if we divide by whatever is the variance, finally we'll get the variance as 1. So this is your mu, this is your sigma square. So now we have this ZI. So we came back to ZI. Where are we going with this? So this is your ZI, because your chi-square test, finally the test statistic should be measured in terms of standard normal distribution. So this is your ZI. That's what we did, ZI, standard normal distribution, and the square of those is your test statistic. So we found out that for categorical data, it can be modeled as multinomial, and multinomial as n increases, as n becomes very large and tends to infinity, this multinomial can be approximated as a normal distribution or a Gaussian distribution with the mean and the variance same as whatever you are getting from the multinomial data, okay, from the multinomial distribution. And then we standardize that with the help of the z-score, which measures distance of a data point from the mean. We standardize it, that is mean centered and variance scaled, and after that we have the ZI. But there's one catch for this, is what Pearson did. So there is a lot of mathematical proofs for this chi-square test, that this variance I, okay, instead of using this variance I, what Pearson did, that he provided a proof. I will not provide you that proof, that this can be written as square root of EI. Instead of variance, I can use it as expected value of EI itself. So there is a proof to make, he did for to make the math simple. I'll not discuss the proof here. Okay, but let's assume that instead of variance, he just put the expected value of E back here to make the math simple. So now my Zi becomes this for multinomial distribution, which is approximated as a standard as a normal distribution, and from there we standardize it, and then this is your standardized standard normal distribution, and this is your basis of your, now we use this as the basis of your chi-square test statistic. So what is your chi-square test statistic? So this is your fancy x square chi-square test statistic. So what does your chi-square test need? It needs your n such standard normal distributions, and it just squares them. So we have the Zi value. If we square them, we'll get the, so we have got the Zi formula, and if we square them, we'll get the chi-square statistic, and that's what it is. Simple. So chi-square statistic is given as I'll use another color. Chi-square, this is calculated. Okay, this is a test statistic found by squaring all the Zi's that we have got, and this is equal to sigma Zi square. Zi is this, plug it here, sigma. So for if the number of categories is k, then I is equal to 1 to k, and this is OI, the count, observed count of ith category, minus EI square, and this EI square root will go off, and this will become EI as it is. So this is your chi-square test statistic. So now we have formulated a categorical data into a chi-square test statistic, and this chi-square test statistic follows a chi-square distribution because of this, and now we can use this test statistic for our chi-square test. I hope this is clear. Okay, so this is your chi-square test statistic also. This is your summation of this, and we found out this Zi, and we plugged in the value here for our categorical data, and we got this formula, and this is the formula that is used. Okay, so now let's, and this is for very large n, the chi-square test statistic. This also for very large n as n increases. So just I'll write a note. For very large n, this chi-square statistic, chi-square calc follows chi-square distribution if the number is very large, and for practical purposes this is considered as 5. Okay, so the expected value or expected count is considered here only. Okay, so the expected value of this count should be greater than or equal to 5 for any category. So this is the minimum value, so it should be greater than or equal to 5. Only then this approximation to normal distribution holds. So expected value for any category, ith category, should be at least greater than or equal to 5. Generally we take it 10, but 5 also holds, and this value is used. Now this is the what makes it a large sample. So this expected value should be greater than or equal to 5 for this multinomial approximation to a normal distribution. This is the criteria, that expected value of I should be greater than or equal to 5. Now we have the test statistic in hand. We understand chi-square distribution. We understand chi-square test statistic. Now let's understand the chi-square. Now it will be easy. What is the chi-square test? Now you have got the hang of it. So what is your chi-square test? So we'll discuss about the two tests. As I said, this is a non-parametric test. This is, you have heard, this is a non-parametric test because till now we have not assumed anything about the parameters of the data. I have not discussed about what is the mu or sigma square of the data. I'm just talking about the count of the data, OI, or the expected value of the count of the data. I'm not talking about the mu or sigma square anything of the data. Okay, because of central limit theorem we have approximated it for very large number, but I have not assumed anything about the underlying distribution or the data. So that's why this is a non-parametric test. Okay, I hope that is clear. And this is for comparing non-negative values. Okay, non-negative values, that is counts of categories. Okay, so whenever you have categorical variable, right, so this will be for observed counts of categorical data. We'll do an example, then it will become, I'll do a problem. Okay, and this requires large sample size. So as I said, this requires large sample size. So these are the things that you should know about chi-square test. This is non-parametric. Okay, so let's get into the first important test, that is goodness of fit test. So what is goodness of fit test? So whenever you hear goodness of fit test, means we are comparing two distributions. Say for example, I have one distribution. So I have one distribution, sorry, any distribution. So I have one distribution, say normal. Okay, I think, okay, from the data we feel that this is a normal data, and now we will see that whether whatever the data we have, does it actually fit a normal distribution curve or not. So we assume that, we make a hypothesis that, this is a hypothesis test, right, that this should be a normal distribution from the observations that we have for the count of the data, and then we try to fit it on the existing PDF or PMF of a known distribution. That's why this fit word comes, that we are trying to fit a distribution, the observed distribution, on the known distribution. So that's why this fit word comes, that how good this is fitting on a known distribution that we have, any distribution. I'm giving you normal because you know this. So any kind of distribution which is known, we try to fit the observed data based on the categorical count, and we try to fit it on the known distribution. Okay, so what is the goodness of it? Used to compare observed frequency count. So let me write it formally. It is used to compare observed categorical frequency count, whatever frequency is the count, observed frequency count of a category. Say for example, if I have a male, female, others, gender, right, so I will count for each category what is the count, the observed frequency of each category count of a categorical variable. Okay, to a hypothesized, okay, to a hypothesized or expected distribution. So I expect my distribution to be normal or any other distribution or t distribution, something variable, to a hypothesized or expected distribution. So I expect it to be certain distribution because the data I have I have observed. So I feel that this should be this, and now I can use this test to confirm whether the expectation and the data, they fit together or not. This is what it will give me. So this is a goodness of fit test, and the test statistic that we are using here is the chi-square test statistic that we have seen already. So test statistic is this one. So copy it as it is and paste it here. So this is your test statistic. Okay, let me make it different color. And what are these values? I have already mentioned, but I'll just write it formally for you. So OI is the observed count for ith category, and EI is the expected count. So we have I is equal to 1 to k for k categories, and then k is the number of categories. Okay, and now we have degrees of freedom also. So there was a parameter n, if you remember, here in the chi-square, right, in the chi-square this thing, distribution, this is n. So we also need this n. What is the degrees of freedom for this? So the degrees of freedom for this would be, so I'll write degrees of freedom is equal to, this is your k is the number of categories, so this will be k minus 1. You have seen this k minus 1. There's one more thing called minus m. Okay, generally this is equal to 0, and this m denotes the number of parameters estimated from the sample data, okay, to determine the expected probabilities or something, okay, or distribution. What is the distribution? So this is the number of estimated parameters estimated from sample data. This is the number of parameters estimated from sample data, okay, to determine the expected probability distribution, to determine expected probability distribution. Generally this m is 0, we don't estimate any parameter, so we'll keep mostly this will be 0, and then this will be your number of categories minus 1. As discussed, the degrees of freedom will be the number of independent observations that will be impacting the variability of the data, okay, observations or data points, okay. So this is your chi-square goodness of fit test. So if you're since we are talking of goodness of fit test, let me tell you some more goodness of fit test. So there are other goodness of fit tests also. They are very popular, and that needs to be, this is for categorical data. What if you have a continuous data, okay, that is more normal? So for that, the most common is your case test or Kolmogorov-Smirnov test or case test. This is used for, so what does it use? It uses your CDF or empirical CDF to the theoretical CDF. So basically it uses CDF. CDF is your cumulative distribution function, the summation of PDF. Okay, it compares the using CDF of two distributions, roughly speaking. And the second one is Anderson-Darling test. Anderson-Darling. These are name of scientists or mathematicians who developed these tests. This is called AD test. So this is just an enhancement of the above case test. Okay, and then we have one more test called Shapiro-Wilk test, or called SW test. So this is generally used for, this is specialized for normal distribution. When you want to compare whether a distribution is normal or not, then we use this Shapiro-Wilk test. This is specialized for normal test. So when we know that the data is normal, so this is specialized for normal test, then we go for Shapiro-Wilk test. But if we don't, if you have any other kind of other test, so mostly we start with this case test, Kolmogorov-Smirnov test. Okay, so these are also tests. Just look at the Wikipedia page, and that will be like self-explanatory. So you will get a broad idea what it is. I just mentioned it because you should know that that is the chi-square goodness of fit test is not the only test, and that too is only for categorical data. And for rest of all the continuous data, you have this. Okay, so this is all around your goodness of fit test. So now we have talked a lot about goodness of fit. Now let's understand it using a question. I'll give you a very simple question. This will make you very clear. Okay, so we are talking about multinomial. So we'll just see a simple case of that. That is binomial distribution. The simplest is toss a coin. We toss a coin, okay, 100 times, and we get heads for say 62 times, and tail is the remaining 38 times. Okay, and now I want to find whether it's a fair coin. I want to find whether it's a fair coin. So what are we asking here? So what is the underlying distribution for a fair coin? It is a uniform distribution, right? That probability of 0 and 1. Okay, even if it's continuous, so this is half of, and if we are doing continuous, then this is 1. Okay, so every value between 0 to 1 has equal probability. So this is a uniform distribution. So we want to confirm whether this observation follows a uniform distribution or not. And here the uniform is only for 0 and 1, but it can have a whole, or it can be for continuous, it can be like this, or if you have a PMF, then we have like this. Okay, on 0 we have half, and on 1 we have half. So this is your PMF. So these are the two masses, and if it's continuous, then this will be like this. This will be 1 with the value here, and 1 is the breadth, because the area under the curve should be 1, total 1, not half. Area under the curve should be always, for PDF, should be 1. This is continuous uniform, and if it's discrete uniform, then the sum of all the probabilities should be 1, and this is half here and half here, so this will sum up to 1. So the basic idea is that it is a uniform distribution or not. We want to confirm that, and for that we'll use the goodness of fit test. So let's see what all values we have got. So we'll do a hypothesis testing. So what is your null hypothesis? What is a null hypothesis? That both are same, means both the heads and tails is same, and it's a fair coin. Fair coin means status quo. Okay, nothing. So my probability of heads is equal to probability of tail, so that is equal to half. So whenever you have equal condition, that's your hypothesis, or null hypothesis by default. And the alternate hypothesis is that not a fair coin, right? So that's what, if it is failing, then it will not be a fair coin. This is your alternate hypothesis. So what is my expected value of I if it is a fair coin under null hypothesis? I'm assuming this is, everything will be under null hypothesis only. All this OI, EI, okay, this is all is under null hypothesis only, under H0, assuming H0 is true. Okay, null hypothesis is true. So EI under null hypothesis, if it's a fair coin, then it should be equal to half, or have 100 times, right? So this expected value should be 50, that is 0.5 into 100. Half of the times should be heads if it's a fair coin. That's the expectation I have, because that's my null hypothesis. But what is the observed? Observed is that observed heads is 62 and observed tails, these are the two categories, I 38. This is the value, right? So we have two categories here, I is equal to 1 and I is equal to 0 and I is equal to 1, or I is equal to 1, I is equal to 2. These are the two categories, and these are the two observations. Now let's put it to the chi-square test. Chi-square calculated. Okay, this is equal to, and here degrees of freedom will be equal to no parameters we are doing. So number of categories is 2 minus 1, that is equal to 1. So chi-square test for 1 degrees of freedom, this is equal to sigma I equal to 1 to k OI minus EI whole square by EI. This is equal to, so we have two categories. So this, let's do one by one. So observed value for heads, so we'll have heads and tails. So we have 62 minus expected is 50 whole square by expected value of I is 50 plus 38 minus 50 whole square by 50. So this is equal to, this is 62 minus 50 is 12, this is 12, this is 144, sorry, plus 144, both the denominator same. I'll put this here, and if you calculate this, they should come out to be 5.76, simple maths. So this is your test statistic. Okay, this is your test statistic. So 5.76 and degrees of freedom is equal to 1. So now we have to see and say, so this is your what we have done. What we have done, that we have our null and alternate hypothesis, and we decided that we'll go with the chi-square test because it is a goodness of fit test. And then we found out the test statistic value. And the next thing we need is the alpha. So let's say alpha is equal to 5% or 0.05. That's my significance value. Okay, significance level. Go away. significance level or value. Okay, that is my significance. So this is there. So now let's find the p-value or the critical p-value or t alpha for 0.05 and degrees of freedom is equal to 1. So we'll refer a chi-square table. So if you just search online chi-square table, you will get it. So let me see. So this is your chi-square table. This is a chi-square table. So I've just highlighted this here. So for chi-square 0.05, it is telling you what is the area under the curve here, right? It is showing you. If you see, this is highlighted here. Okay, this chi-square. So for chi-square for 0.05, for degrees of freedom, this df is degrees of freedom 1. So this will be 3.841. Okay, so let me take a screenshot. I can highlight it for you. Okay, let me paste it. So let's come back to the screen. Okay, so what is our alpha here? So let me make it bigger if it's not clear. So here if you see, my alpha here is 0.05. So this is the value. So let me highlight all of them. So this is your 0.05. What is the corresponding degrees of freedom? I have 1, and this is your 3.841. And here it's showing that this is the value under the curve. Okay, so I hope this is clear. This is a way to see. You just write chi-square table and you will get this. So for degrees of freedom, we got that the value should be the T alpha, the critical value. The critical value for this is equal to 3.84, and we'll just plot this way. This is right skewed. So the critical value here is 3.84, and we have got our p-value as 5.76. So what does it say? So my p-value here is this region. This is equal to probability of observing t greater than or equal to t observed. This is chi-square value in our case, and this is your critical value. Let me use a different color. So this is your significance level. Okay, so this value should be 5%. The area under the curve here is 5%. So definitely the area under the curve is less than 5% here. So it is not meeting the criteria. It is less than the significance level. So it is not so significant. So what we will do, we will say that we can reject the null hypothesis. Okay, because my p-value is less than alpha. This is your alpha, which is 0.05. So what was my null hypothesis? That the coin is fair. But from the observation and whatever the chi-square test says, that no, reject the null hypothesis, accept the alternate hypothesis that coin is biased. This is not fair or not fair. I hope this is clear. Okay, this is clear. It's very simple. So we just did a test for whether it's a uniform distribution or not. Simple test. Okay, so this is your chi-square test of goodness of fit test. Okay, now let's quickly do the test of independence also, because it uses the same test statistic, everything, so it will be pretty fast. So what does it do? Chi-square test of independence. Okay, so we'll discuss about test of independence. So this is to find out whether two variables, two categorical, again categorical variables are independent or not. So how do we do this? So whether some association exists between two variables, whether they are dependent or independent, that's what it tests. So chi-square is non-parametric as usual. It doesn't take into account the parameters mu, sigma, etc. So it uses the same test statistic and it just extends that thought. It just compares two categorical variable to find whether they are independent. So what do they do is here that, so the test statistic remains same. So what do they do that? They put the two categorical variables in a tabular format. So what do they do? So they will create a table like this, and they'll put all the observations here. Say for example, if I have two variables, one is x, one is y. So I'll put one towards the in the row, x will be here, and y will be in the columns. Okay, and we'll get a combined probability. So we'll put all the probability values here. Okay, for each one of them. So this will be like xi, yj. Okay, whatever is the value. And using these values, I'll put it in this table, and from all these values that I have, I'll find out whether these two are dependent or independent. Very simple test. I'll use the same statistic and I will just find out. I'll give you the details how we'll find out, but this is broadly the thing. I'll put all these values, and then don't you see this is like a covariance matrix? Okay, so generally this is giving your variance and this is like covariance. So this is giving you the relation between two variables, and each cell will have some value, and using these values we can compute the final result, whether they are dependent or independent. We just put them in a, and this table is sometimes called, generally referred to as contingency table. Generally contingency table means like dependency table. So we try to find out whether they are dependent or not. So this table, when we put this data, that is called contingency table. Okay, and the test statistic here is a bit modified format of the chi-square only. There we had only single variable, and now we are having two variables together, because one was known, other was unknown here, and here we have both are unknown. So we'll take both of them into account, and then test statistics becomes x square calculated is equal to summation over both row and column. So I equal to 1 to r, and j is equal to 1 to column value, and then same thing. This will be the OIJ and EIJ for each I and j. So I will be moving from 0 to r, and then j will be moving from 0 to c. So each cell will have values like this here, OIJ, EIJ. Okay, we'll see how to compute that. So it will just compute the OIJ minus EIJ whole square by EIJ. So it's the same thing. It is just across this complete table that we got x and y. We put them together, and then we are trying to find it. So we are trying to do a test of independence. So now let's revise our basic probability. If two random variables, if they are independent, then what can we say? If a and b are independent, what do we say? That p a and b is equal to p and a into b. This is also written as p a like this, p a b, or joint probability is equal to the product of individual marginal probabilities. So simply put, the a and b is p a and p b because they are independent. This is your simple test of the formula for independence. Okay, so now let's do the test. Okay, so what is a null hypothesis? So we'll put it in the terms of hypothesis testing. So null hypothesis is that variable a and b here or whatever are independent. So there is no change or nothing, no impact of each other. So that's your default null hypothesis. And H alternate is that variable a and b are dependent. If the null hypothesis does not hold, or if it is rejected, only then we will come that no, they are dependent. Okay, and then let's define all the variables. R is equal to number of rows, C is equal to number of columns. Okay, in this table that we have put all the values so that we can compare. I'll give you an example after this that will make it very clear. And now let's calculate all these P probabilities so that we can compute. So probability of A of I is equal to, what will be? for this ith, so all these are categories. So I0 to R, this is like category. I'll put it as 1, okay, for simplicity, because these are categories. So each row will have one category and each column will have one category. So these are two different variables. So for example, okay, so this is gender, male, female, two categories, and this is the type of drink. I'll give you an example also, whether they drink tea, coffee, or soup, or just milk, something like that. So I can have different categories on this. So I have one category as tea, one as coffee, one as milk, one as soup, one as juice. So these can be different categories. Is there any relation between these categories and the gender, male and female? Like if male, female, certain categories, and female prefer certain categories, is there some relation? Are they dependent or are these independent? So that's what we'll try to figure out from this test. Okay, so these are the categories. Each column is a different category, each row is a different category. So probability of AI, probability of the ith category for A, this is A and this is B. So instead of X and Y, I'll write the consistent notation. This is A and this is B. Say on the row I have A and on the column I have B. Let me highlight this so we don't confuse. Let me use another color so that it is not lost. We'll come back and refer again. So what will be my probability of ith category, and say my total number of samples I have is n. So n here, n is equal to total number of samples. So probability of AI will be row total of the ith category by n, okay, where n is the sample size, this is the total number of samples. Similarly, probability of BI will be column total of the ith category by n. Now what will be the expected value? Eij is equal to the cell value for this expected value here, any ij, this is I, this is j. So I expect them to be the product of these two. So this will be equal to, and expected ij for all the cells will be n into probability of AI into probability of bj, because there will be n cells, right? R into C, there will be n cells. Okay, how do we reach to this formula? Okay, expected value. So this will be here. So now let's do this. So n is here, okay, and then row total I into by n into column total I by n. This is the expected value for ij. So this n and this n cancels out. So finally my Eij will be row total of ith, and this will be j, sorry, this will be j, this will be j, okay, and j I'm using to measure count here the columns. Row total I, column total of j by n, because only one n remains here, okay, and my Oij is the, so these are the all the variables I'll declare only, and Oij is the observed count that I'll get from the data itself. That is the observed count of ith category. Okay, so I have defined all the required variables, Oij, Eij, that is the main thing, and R and C. R and C for what is my test statistic. So this is my test statistic here, and plus I have degrees of freedom is equal to, this is equal to again sorry, this is equal to R minus 1 into C minus 1, because we have found out that only n minus 1 variables can vary independently. The nth variable is dependent on other n minus 1 variable. So my degrees of freedom which can change independently are n minus 1. So R minus 1 for the rows and C minus 1 for the columns. And so this will be my degrees of freedom. So now I have all the data, because this will be used, this degree of freedom will be used to see the chi-square table. And this will give me the test statistic value. And what is my null hypothesis? That variable are independent, and the alternate hypothesis is that this is dependent. So now based on all this information, let's solve a small problem and this will set everything clear. So let's do a question quickly. So the question is, we survey, again whatever example I will just carry the survey, n is equal to 100 students. I'm surveying 100 students to find out what is their preferred beverage, and I'm categorizing them on the basis of their gender, male and female. So I'm surveying 100 students, and I'm finding their beverage preference. What is their preferred beverage, tea or coffee? And the categories are male and female. Okay. So I'll create the contingency or the dependency table. So I have gender on one side. Okay. And this will be, okay, let me put it. So we have, sorry, tea here, coffee here, and we have male here, female here, like this. Okay, and we have the numbers. Okay, say for example, these are the this is my on the A side, and this is my B variable. Okay, this is a variable, this is a B variable. So I have to find out whether these two variables are dependent or not using my chi-square test of independence. So let me put where these are the observed values. This is the data that you have been given. Okay, so what is the variable? That 20 out of 100, 20 like this, 10 like this, 30 like here, and 70 no 70 no 70 is the total, 40. So I'll just draw one more line here and one more line here. So what is the total number of males? 50. Total number of females? 50. Total number of people who like tea only, this is 30, and total number of people who like coffee, this is 70. So total number of males is this is a AI, this is a A1. So if you write the cell, this is 1 2 1 2, so this will be 1 1, this will be 1 2, this will be 2 1, this will be 2 2. Okay, so all the values, this is observed. Similarly, we'll compute the EIJ also. These are the observed values, O11, O12. So this is the I is varying from 1 to 2, and J is varying from 1 to 2 here, this side. This is your data. Now let's put that into the statistic. So what will be the, first of all, degrees of freedom? This will be equal to R minus 1 into C minus 1. So this will be 2 minus 1 into 2 minus 1. This is equal to 1, 1 and 2 1. And what will be my chi-square for 1? This will be the formula sigma I equal to 1 to 2, sigma I equal to 1 to 2 for rows and columns. Then OIJ minus EIJ whole square by EIJ. Okay. So let's set this up, and then what is my null hypothesis? That nothing is changed. The gender preference are independent. Okay. So this is a hypothesis test. So my null hypothesis is that gender and beverage preference are independent. And what is my alternate hypothesis? No, gender and beverage preference are dependent. So all the tests will be performed on the null hypothesis itself, and all the observations will be made based on the null hypothesis. So let's calculate them. So all the OIJs I have, OIJs these are the observations. Now we have to calculate the EIJs. So E11, E12, E13, E11, E12, E21 and E22 needs to be calculated. So what is your EIJ formula? So this is your row total ith into column total jth by n, total number of this. So let's do E11 is equal to row total of 1. So I'm doing of 1 and column total of 1. So first row total of 1. What is the row total of 1? So this is a row total of 1. So this is 1 from A side. This is your A and this is your B, I and J. So 20 plus 30, this is 50. So row total of I is 50. And the column total for I, that is first one is T, this is this side, this is 30, and this is into by 100. Similarly, E12, so A is 1 and B is 2, so this one. So A will remain 50 itself because this is coming from here, and this is 2. So 2 is 70. This is for coffee. This is your second category from B side. So first category from A side, which is male, and second category from B side, which is coffee. So this is your E12, which is 50 into 70 by 100. Now E21 is equal to, now second category from A side, that is female, and the first category from T side. So what is the sum of this? This is 50 again. This is the row total of this second I is equal to 2, and the sum total of T, or the first column, is 30 again. This we know. So now we remember all this. So this is 50 into 30 by 100, and similarly E22 will be equal to 50 into 70 by 100, because again this will remain 50, and this sum for coffee will be 70 only. Okay, let's do quick calculations. 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0. So this is 5 3s are 15, this is 5 7s are 35, this is 5 3s are 15, and this is 5 7s are 35. And now let's put all these value in my chi-square calculated. This is equal to sigma I equal to 1 to 2. So we'll just put all these values together. Okay, no, sigma I equal to 1 to 2, sigma I equal to 1 to 2, and then let me write the formula so that we don't forget it. Okay, so this is two categories are there. So E11, E12. So OIJ for first one is 20. This is the observed value, 20. I'll just put 20 minus 15 E11 whole square by expected value 15. Similarly, E12, this will be 30. Sorry, 30 here. This is the observed value. O12. I'll write the values, then you can find out. This will be 30 minus 35 whole square by 35 plus 10 minus 15 whole square by 15 plus last one is 40 minus 35 whole square by 35. This is the expected value, right? 20 minus 5, all is 5 differences there, right? 20 minus 5, 30 minus 5, 10 minus 5, 50 minus 5. So all is 5. So this is 25 by 15 plus 25 by 35 plus 25 by 15 plus 25 by 35. Do the calculation, and this will finally come out to be equal to 4.76. Okay, degrees of freedom we have calculated. So DOF is equal to 1. So now let's see the critical value. Now let's set this. So we have null hypothesis that gender are independent, and alternate is that they are dependent. We have calculated the test statistic. We have the value now. We use the chi-square test of independence. That was our choice of test. This is a test statistic value. Now let's set up the alpha, that is 5% only, that is 0.05. This is the next step, and then let's calculate the p-value, or let's p-value for this. P-value we have this. Okay, here. Let's find out the critical value for alpha. So we'll find out the critical value so that we can find out critical value at T alpha. So this is for 5% and degrees of freedom 1. So we need to find chi-square for 0.05 and degrees of freedom 1. I think we had the same value last test also. So let's check. Yeah, same value. So I'll just show you same thing. So we have this, right? So let's come back. So we had the same alpha last time also, and the degrees of freedom was same in this also. So we'll again get the same value, 3.84. Okay, let's come down. So the t critical value for against this will be 3.841. Okay, and now since, so we'll plot it. Let me show you again so that you get used to it. So where is my critical value? This is your 3.84, means the area under the curve. This is your 5%. This is equal to your alpha significance level. Okay, and what is my p value? The t observed. The p value I cannot get it from. I can plot this 4.76. So 3.84. So 4.76 will be somewhere here. So definitely this area is less than. Okay, this is less than 5%. So it is less than the significance level. So if it would have been greater than 5%, say 7% or 10%, then we would have accepted this. But this is less than the significance level, means this is not so significant. Whatever we have, whatever data we have got, this is not statistically significant. So based on this, finally we will reject the null hypothesis, that, and then we will accept the alternate hypothesis, that gender and beverage preferences are not independent, but they are dependent. So from chi-square test of independence, we found out that both are dependent. I hope this is clear. Now this example must have made this test of independence very, very clear. Let's do a quick revision. We have done a lot of things, so just a quick revision will help. So we are discussing chi-square test. Okay, within that we saw first the chi-square distribution. So we should know what is chi-square distribution. So this is nothing but a distribution of the squared, okay, squared normal, standard normal, independent distributions. Okay, so these are independent, n independent distributions, which are standard normal distributions, and if I square them and if we plot them, the distribution that we get, that is called a chi-square distribution. So this is what we'll use as our test, underlying test distribution. So we understand what is a distribution now, and we have seen, and within this, and this is defined for degrees of freedom, we understood what is degrees of freedom. Say for example, if you have 10 observations and their sum is 50, then only the 9 observations or data points can change, because the 10th is dependent on the other 9, because the sum is fixed. So whatever 9 data points we choose, the 10th one will be fixed, because this sum of 9 other data points will remain constant, and this cannot be independent. For example, if my sum of other data points is 45, then this will be 5 only. It cannot be 7 or 10. So this is dependent on the other 9. That's why this is their degrees of freedom. So this is your n-1 for n data points. Okay, these are degrees of freedom. Then we delved into central limit theorem. From there we found out that if the mean is normally distributed, then also, and mean is average is equal to sample mean. This is mean. This is sum by number of samples. So even the sum will be normally distributed from this way, sum or a count, because chi-square test is for categorical data, and where we have count of the data, we have the observed count and the expected count, and we compare that. So that's why from this we figured out that even the sum or count will be normally distributed, and that's what we will use further. Then we found out properties of chi-square distribution. We came back to this, that it is non-negative because it is sum of squares, and it is skewed towards right. Okay, and its shape depends on degrees of freedom, and then we saw the shape also. If you see, and if n becomes very, very large, this will become like a normal distribution. Okay, then we figured out that for categorical data, which is a multinomial distribution, and for multinomial distribution, the expected value and the variance, everything we took from the formula, and we found out that if for very, very large n, as n becomes large, this observation count, the observed count which we have, this can be approximated as a normal distribution or a Gaussian distribution with the same mean and variance of the multinomial distribution. and from there we came, because now this is normal, now we can move to the normal zone. So we found that let's calculate the z-score for the standard, because this is for the standardized data. So we standardized it and we found the zi for the, which is z-score, which is the measures the distance in terms of standard deviation from the mean. So we standardized it, that is mean centered and variance scale. And then we found out that instead of square root of variance, Pearson suggested a mathematical hack which made the computation easy, and instead of variance we used expected value itself, and this will be a zi. And this zi was used as it is for the chi-square test, and because chi-square test uses the square of a normal distributed standardized normal distribution which is having 0 and 1 as mean and standard deviation, and it used this, and we just plugged in those values, and from there we got the chi-square test statistic, that is OI minus EI whole square by EI. Okay, so this is clear. And we use this test statistic for doing our chi-square test, which is a non-parametric test, because it doesn't assume anything about the underlying parameters mu or sigma square of the data that it has, or any other parameters. So that's why it's a non-parametric test, and it just compares the non-negative values. Okay, that is the observed counts of categorical data. That is, chi-square test is used for categorical data where we have the observed counts, and all the test is based on that. So it requires a large sample size for functioning well or giving good results. So we discussed about first thing is goodness of fit, and where goodness of fit means we have the observed count, we hypothesize that it will follow a certain distribution, and we try to find out how good the two fits are, the observed data and the hypothesis or expectation that we have. This should be normal, so how good my observed data fits into this expectation. So that's why this goodness of fit, that how well it is fitting to a known distribution with the parameters that we are giving. Okay, so it is used to compare observed frequency count to a hypothesized or expected distribution, and the test statistic remains the same. Okay, OI is observed count, EI is expected count, and this is the expected count as it is. K is the number of categories. From this we calculated degrees of freedom, and we have one more term, k minus 1 we know, but we had one more term, that is m, which is the number of parameters estimated from the sample data. But generally this is 0 for our practical purposes, so we won't dive into that. Okay, don't worry about this. And there are other goodness of fit tests also, because this is only for categorical data. What about continuous data? So there are other tests. The most common is case test or Kolmogorov-Smirnov test, where we compare empirical CDF, basically the CDF of two, or CDF of the underlying CDF of the data, to find out whether the two distributions fit well together or not. Okay, whether they are having good fit or not. So that is there. Then we have Anderson-Darling test or AD test. This is just an enhancement over case test. And then we have Shapiro-Wilk test or SW test, which is specialized for normal distribution. So these are other goodness of fit tests, okay, which you should know. Just check the Wikipedia. And then we move to, and then we saw coin toss example. Okay, and from there we found out whether the coin toss data we have, whether it forms a uniform distribution or not, whether it fits a uniform distribution or not. And then we move to test of independence. And there, while doing this, we also learned how to see a chi-square table. So this is a chi-square distribution table. From this we read the table also, how to read it. So we found the critical value beyond which my value should be, and we rejected it. So we learned this also. So it is a hypothesis testing. So we learned to see a few more tables now. And finally we discussed chi-square test of independence, which compares the dependence or independence of two variables, and we put the values in a tabular format, which is called a contingency or a dependency table. Contingency means dependency. So we put this, and all the categories come in for one variable along the row, and for others it comes along the columns. Okay, and all these values are there, and we again compute the observed value that comes in the data itself, and then we compute the expected value for each of them. We saw how to compute that, and we also revisited that if two variables are independent, then P intersection B is PA into PB. Okay, the joint probability is the product of marginal probabilities. Okay, and then we found the formula. So the statistic test was, we put the formula somewhere. Yeah, this one. Let me highlight this. So the degrees of freedom is r minus 1 into c minus 1, and then this is the same thing. It is summed over the complete all the cells of this table that we get. This is I1 to r and j1 to column. So this is sum over all the cells in this matrix that is formed, and we compute for this zi square for all the cells, and then we find out what is the final value. And then we saw one example where we compared the gender and the beverage preference and whether they are independent or not, and finally we found out that no, they are not independent. We rejected the null hypothesis and we accepted the alternate hypothesis. Okay, so this is all about chi-square test. I hope this helps you. That's all for this video.